días, señoras y señores. Gracias por acompañarnos el día de hoy al webinar internacional El Marco y Desarrollo Reciente para la resiliencia entre desastre y la inteligencia ante el desastre y la inteligencia de riesgos. Por favor, aquellos que se están conectando a través de nuestra plataforma Zoom, les rogaría que puedan realizar el cambio de idioma. Justamente vamos a proyectar en la pantalla, hemos estado colocando en la pantalla sin ayuda el área de soporte para que puedan hacer el cambio de idioma al idioma español. Igualmente, aquellos que nos están escuchando o se están conectando por nuestra transmisión en vivo por el Facebook, igualmente puedan tener la opción del idioma. Así que muchas gracias por acompañarnos y para iniciar en estos momentos vamos a presentar con ustedes, permítanme. Quisiera dar la bienvenida para las palabras al doctor José Macharé Ordóñez, quien es presidente del Comité de Riesgo de Desastres de la UEFPEO. Bienvenido, doctor Macharé. Adelante, por favor, con su presentación.
Good morning, good afternoon, good evening to everyone. We started this year with our first webinar from the Committee on Disaster Risk Management of the World Federation of Engineering Organizations. As a brief introduction, the WFEO it's a federation bringing together engineering organizations of more than 100 countries and of all the continents and a large oceanic area too, representing about 30 million engineers around the world. One of the main objectives is to advance, to contribute to the advancement of the sustainable development goals from the engineering, from our profession. And the Committee on Disaster Risk Management is one of the technical, standing technical committees focused mainly in the SDG 11 concerning resilience and sustainable cities and societies. Today, we have invited speaker, Dr. Yoon Ho Son, that will be presented immediately. For this, I invite Dr. Valentina Cutrino, representative from the UK in our committee and vice chair of the leading the committee, the working group on capacity building of the CDRM. Valentina, please, for your introduction. Thank you.
Thanks, Professor Jose. Good morning, good afternoon, and good evening to our audience. Whichever is your current geographic location, I'd like to thank you as lead of the Capacity Building Working Group of the CDRM for joining us today. It is a great honor for me to moderate the webinar entitled Framework and Recent Developments for Disaster Resilience and Risk Intelligence, delivered by Professor Yoon Ho Son from the Department of Civil and Environmental Engineering of Seoul National University in South Korea. Professor Song obtained his PhD in Civil and Environmental Engineering from the University of California at Berkeley, US in 2004. After working as a postdoctoral researcher at UC Berkeley and a senior vulnerability engineer at Risk Management Solution, he joined the faculty of the University of Illinois at Urbana-Champaign, US, where he served as assistant professor, associate professor, and CEE Excellence Faculty Scholar. In 2014, Dr. Song joined the faculty of the Department of Civil and Environmental Engineering at Seoul National University as a young scholar for the next generation. At SNU, Dr. Song served as associate professor, associate director of education and research program of InfraSphere, and associate dean of academic affairs. Professor Song has research interests in structural and system reliability analysis, reliability-based design, topology, optimization, and decision-making risk, reliability and resilience analysis of urban communities and networks, earthquake engineering and random vibrations, and statistical machine learning for urban infrastructure systems under uncertainties. His academic duties span far beyond the canonic remits of the great scholar that he is. His technological innovation in the area of seismic reliability and optimization were recognized by awards including the IASSAR Research Prize during the 10th ICOSAR conference in 2009. Professor Song has been serving as a member of the Probabilistic Method Committee of ASHE Engineering Mechanics Division, 5 editorial boards of international journals, the Subcommittee of International Association for Structural Safety and Reliability, Joint Committee of Structural Safety, and the Board of Directors of the International Civil Engineering Risk and Reliability Association. Dr. Song is currently the president of CHERA and the chairman of the IFIP Working Group 7.5 on reliability and optimization of structural systems. Today's webinar by Professor Song first introduces a system reliability-based disaster resilience analysis framework, which was recently proposed to evaluate the holistic capabilities of civil infrastructure systems, such as structures, network, urban communities, in terms of 3 criteria: reliability, redundancy, and recoverability. Method and tools developed to promote probabilistic evaluations of disaster resilience, considering components, system, and their interrelationship, are also presented to illustrate how stakeholders can check if the system-level disaster resilience is socially acceptable and identify optimal decisions. The framework and methods are further demonstrated through application to real infrastructure systems, such as a cable-stayed bridge under fire hazards and transportation networks subjected to earthquake hazards. The second part of the webinar discusses the concept of risk intelligence, which Professor Song is promoting as a future paradigm of risk management of civil infrastructures against rapid urbanization, globalization, population growth, and climate change. To achieve data-driven, automated, holistic, and real-time risk management, 4 elements of risk intelligence, which are identification, integration, inference, and implementation, are identified and discussed from the viewpoint of data information knowledge flow. Recent research development are also presented to illustrate the 4 elements and identify further research topics that we need to investigate to achieve risk intelligence in the future. And now, without further ado, I leave the floor to Professor Song and invite you all to post your questions in the chat box, which will be answered at the end of his presentation. Thank you very much.
Okay, thank you very much, Professor Jose, for inviting me to this webinar. And also many thanks to Dr. Pucherino for inviting me and also the nice introduction. I'd like to thank the World Federation of Engineering Organizations and its Committee on Disaster Risk Management for this opportunity to share my recent research development. And also I'd like to thank the Peruvian Engineers Association, which is co-organizing this event. So disaster resilience and risk intelligence, these are the two main themes I have in my research group. And today I'd like to just briefly present some frameworks I'm proposing for these two main themes. And also I will share some recent developments from our research group. So this presentation consists of two parts. So in the first part, I will focus on the disaster resilience. So before I start talking about this disaster resilience, I'd like to recognize the great contribution from my former and the current PhD students and postdoc. They are currently working at the US and also in Canada, and also currently with me at Seoul National University. So in my first half of this presentation about the disaster resilience, I'll first give you some brief introduction about what I mean by this disaster resilience for those who are not familiar with this concept. And then actually I will explain some framework I recently proposed based on system reliability to evaluate and manage the disaster resilience of civil infrastructure systems. And then to facilitate the use of this framework, actually I developed the so-called reliability redundancy analysis method. I use the Greek letter beta and pi to represent this reliability and redundancy respectively. So we just named it as a beta pi analysis using a beta pi diagram. And then I will demonstrate this method through application to a real cable stay bridge in Korea under some fire hazard. So if you look up this word resilience from the dictionary, it's going to give you some simple definition as something you can see in the screen. So simply, usually resilience refers to the ability to become strong, healthy, or successful again, even after something bad happens. And also there are many pictures that try to describe this concept resilience. But my favorite one is the one you can see in the screen. This tree is being bent during this strong wind event, but it's not being broken. So it will actually also eventually come back to the original beautiful shape. So, and also this resilient concept has been discussed and investigated very deeply in science and engineering recently. One of the pioneering work was done by the Holling in 1973. And actually, he talked about this resilience as some sort of alternative viewpoint to the ecological system's ability. So traditionally, they use this stability viewpoint. So here they assume that they can predict what is going to happen in future. And so they want to achieve equilibrium and also some system that has a minimum fluctuation in future. But actually, if you take this resilience approach, like an alternative viewpoint, it means actually we admit that we cannot predict what will happen in future. So actually, instead of requiring some precise capacity to predict the future, they aim at some system that can observe and accommodate some uncertain events in future. In many engineering areas, actually the resilience has been a very important topic these days. And you can find a lot of work from these review papers I listed here. But generally in this engineering world, the resilience is understood as ability or capacity of an engineering system to sustain external and internal disruptions, hopefully without any discontinuity of the original functionality. But if actually there's some discontinuity, we want to recover fully and rapidly. So there are lots of work about this disaster resilience, but one of the pioneering work in the earthquake engineering area was done by Bruno and Reinhold, and they presented this paper in a national conference on earthquake engineering in 2006. And actually on the upper right corner, you can see this kind of plot or function. They call it restoration curve or performance measure curve. So actually, if you look at any papers about resilience, it's very often they use this kind of curve to describe the resilience of a system and also quantify it as well. So usually the y-axis is representing quality of infrastructure or performance level or state of the system. And then as the disaster occurs, the level of this performance quickly drops. And then actually it's going to recover to the original or some different level of state. So actually, for example, they just measure this area to quantify the resilience of a system. But actually, I just remind myself that in their work in 2006, actually they described the resilience by 4 different criteria or concepts, such as robustness, redundancy, and the resourcefulness and rapidity. So even from the beginning of their research or discussion, they actually aimed at some sort of holistic and a multi-aspect understanding of the system's capability against the disaster. So actually, there are many researchers working on this disaster resilience, but my motivations are as follows. Actually, this resilience concept was originally created to describe the capability of some living thing, like an ecological system. But as we all know, the civil infrastructure system is not a living thing. So it means we engineers, human engineers, are kind of breathing in resilience DNA into this civil infrastructure system. So it means if you're doing some research on resilience, you have your own some sort of wish list about the resilience DNA you want to implement into your civil infrastructure system. So this is my wish list, personal wish list. First, in this so-called performance measure or restoration curve, they often use this as a single measure over some different options or decisions. But actually, the definition of this performance measure is often subjective or disputable. And also, we cannot describe this resilience by only one measure. And also, there are lots of uncertainty in the hazard and also response of the system. So we should handle this in a probabilistic manner. Second, the civil infrastructure system is a very complex system, or sometimes system of systems. So actually must have a systems perspective when we evaluate this resilience. But actually, so far, all this analysis about the resilience have been focusing on either components or system only, and also the relationship between the component reliability and the system redundancy is not very well known yet. And third, the reason why we are doing this analysis or evaluation is to make a good or better or optimal decision. But actually, getting some insight from this analysis is fine. But what should we do specifically after this analysis? So I'm just, hoping that we can develop some method and framework such that the result of this analysis or evaluation can be used in our decision-making process regarding resilience of our civil infrastructure systems. So with these items in my wish list, I wanted to build some new framework based on the system reliability concept. One of the reasons why I made in this direction is that actually this is my research focus in my career. So as you can find from the reference information at the bottom, actually in this chapter of the book, I just summarized some research development I made during my PhD study and also my career at the University of Illinois. And at the bottom also, recently, I published some review paper about the system reliability analysis with my former students at Illinois. So for those who are not familiar with the system reliability, if I just describe it in a nutshell, in the system reliability analysis aims to compute the failure probability of the complex system based on reliability of each component, and also statistical dependence between components. And finally, we want to consider some cascading effects in our systems too. So as you can see, this is a very complex analysis. So actually, I developed some method to handle and overcome these issues in this problem. So with this system reliability in my mind, during my sabbatical leave at Carnegie Mellon University, I started drawing some figure that can demonstrate or visualize my view, system reliability perspective on disaster resilience. So actually, I was inspired by this meta stability in physics course. So I believe as an engineer, when you took a course on physics in your college days, I believe you have seen some pictures like this. So then actually, I just consider this ball sitting near the cliff as our civil infrastructure system, whether it's a bridge or lifeline network or our urban community. And as we know, this civil infrastructure system is always under some hazard, and whether it's an earthquake or strong wind, etc. And they are going to push our system down the cliff at some time. We don't know when it's going to happen. So then actually I tried to describe this disaster resilience or capability of this civil infrastructure system using 3 criteria. The first one is the reliability, represented by this red block in this figure. So this reliability refers to capability of the components in our civil infrastructure that can avoid initial disruption. So even if there is some hazard, if you have enough reliability, there will be no significant disruption in your system. So that is the reliability. But actually, we cannot have infinite level of reliability because we cannot afford it. So actually, that kind of damage or some failure will happen. But actually, we want to have some certain level of redundancy. So this redundancy is the ability of our system that can actually prevent this initial disruption from cascading toward the more system level failure or degradation. So that's the light blue color block in that figure. And finally, no matter where you are on the cliff, actually we want to recover this system's performance to the original state rapidly and completely. So this recoverability is a kind of ability of your engineer or society. So actually, with this picture in my mind, actually, I wanted to develop some method to evaluate disaster resilience of our system from the 3 criteria and also from system reliability perspective. So I like to illustrate this framework and the criteria using some real event example in Korea. So you are looking at the Seohae Grand Bridge in South Korea. This is the first composite cable stay bridge in Korea. And also this is one of the kind of busiest bridge because it has around 42,000 vehicles per day. But one day, actually, there was a lightning and actually there was a fire on the cable. And actually, I'm going to give you some details about this incident. So in 2015, December 3rd, actually, one of the cable was actually caught on fire, but the fire was induced by lightning. So this number 72 cable was actually causing this fire in the beginning, induced by lightning. But actually, this cable 72 was very high, located 80 meters above the deck level. So it was extremely difficult to extinguish fire. So it took 3.5 hours to extinguish it. So then, because of that, this cable was completely ruptured, and then it was swung into the other cable. So this cable 56 and 57 got caught on fire too. So they actually suffer from some partial failures as well. So a total of 3 cables were partially or completely damaged. And also 1 firefighter actually passed away, unfortunately. And also there was some huge indirect loss as well, because they were concerned about this performance of this system under some normal traffic conditions. So actually they decided to shut down the traffic completely until they replace this cable by new ones. So they actually thought it's going to take a month, but actually they were able to reopen this bridge in 16 days. So if you look at this event from these 3 perspectives or 3 lenses of this disaster resilience framework I'm proposing, actually, I think we can have a better idea about these three criteria. First, in terms of reliability, actually, these cables did not have enough reliability, although these bridges are susceptible to lightning because of the environmental condition. And also, this bridge did not have a lightning rod. And also, they did not have a capability to extinguish this initial cable fire quickly. So because of this lack of reliability, actually, they started concerning about this redundancy. But fortunately, they did not have immediate progressive failures, although 3 cables were damaged. But actually, they were not confident about this performance of the system under the normal traffic, so they had to shut down this traffic completely. So it led to some huge economic losses. But in terms of recoverability, actually, it was a champion case. Because they were able to replace these 3 cables in just 16 days. The key to this success was that they had enough resources. For example, they were able to find the cables from construction sites nearby. And also they had a good, excellent bridge experts. And also they kept this information about this bridge, including final element simulation models. And also they were able to do this one very quickly. So with this example, I hope that you got a better understanding about what I mean by these three criteria, and also the system reliability perspective on disaster resilience. But I also noted that actually there are multiple scales to which we can apply this framework. So you just look at this structure level. So it means we consider this cable stay bridge as a system, and there are many components like cables and decks. But if you step back, this cable stay bridge is a component in a bigger transportation network in a city. So actually, we can apply this resilience analysis to the network level as well, such as transportation network or power or gas distribution network too. So then actually, by doing this analysis at the network level, you might want to come up with optimal or better management decision for these networks. If you take one step further back, actually you can find the bigger scale, which is a community level, because this lifeline network is also a component of this bigger urban community. So actually by applying these 3 criteria to this community level, you can find some meaningful outcomes as well. So far, actually, I talk about 3 criteria: reliability, redundancy, and recoverability. They are actually capability of the component and the system, and also capability of your engineering society and the community as well. Also, there were 3 different scales: individual structure and network and urban community. So in this paper I published last year, actually, I just named this as a 3x3 resilience matrix. It means there are 9 cells in this table. For each of these cells, you can identify some research needs. But today, because of this lack of time, I'm going to focus on this individual structure level, especially reliability and redundancy of individual structure. So then, in order to perform some actual analysis with these 3 criteria in our mind, actually, we have to have some sort of quantitative measure, such as index. So actually, we invented or reinvented this reliability and the redundancy criteria for the purpose of this kind of analysis. So first of all, reliability index beta is actually related to, please forget about this detailed mathematical expression. You don't have to focus on those details. But this beta can be computed in terms of probability that a certain initial disruption scenario occurs given hazard of your interest. So if you look at this figure on the right-hand side as an example, in this kind of simple system, structural system, you can think about initial disruption scenario like member 2 and 5 fail together. That is one initial disruption scenario, Fi. So then by performing so-called structural reliability analysis, using structural analysis and also statistical information about those random quantities in this problem, and also many algorithms, you can compute this probability. Then you can translate this one to reliability index beta. Okay. Next, this is a new one because we've been using this reliability index beta a lot in this community of structural reliability analysis. But redundancy index is a kind of new index I propose in this paper. And I assigned the Greek letter pi to it because I examined all the Greek alphabet from alpha to omega. And then actually I chose this pi because I found this word pleonasmos, then means a redundancy in Greek, and it starts with the pi. So actually I chose a pi to represent the redundancy index. And as you can see, pi is actually computed in terms of some different probability, that is probability of system level failure given this occurrence of this initial disruption scenario. So if I use this example on the right-hand side, previously our initial disruption scenario was concurrent failure of member 2 and 5. So it means we don't have those members anymore in this simple system. And then this system is going to be less redundant. So then what's going to be the probability that this system is going to be just broken into two parts? One possible scenario is that this member 6 fail because of the load redistributed because of this failure. Or 1, 3, 4, if they all fail, this first layer is also disconnected. So we can compute this system level failure probability by performing so-called system reliability analysis. Then actually you can find out this redundancy index pi. So then we can, for each initial disruption scenario we examine, we can compute this pair of beta and pi, and we can put them in this scatter diagram or scatter plot. So then we are going to have as many markers as initial disruption scenarios that you consider. Okay, so from the previous figure, you just got a one marker, and that's the location in one location in this scatter diagram or beta pi diagram. Okay, so then here, please, ignore these details, but using this pi and beta and also mean occurrence rate of the hazard, you can compute the probability that your system is going to fail because of this initial disruption scenario annually. And actually, we want to control this probability below so-called de minimis risk. It's kind of risk the society accepts without some special regulation. It's kind of some risk we should live with, okay? So in this scatter plot, this red area, actually, we cannot satisfy that constraint. In this white area, actually, we are okay. That means by performing this beta pi analysis for all these initial disruption scenario, we can identify some case or initial disruption scenario that cannot satisfy this condition. Then we should make some decisions or action to move this marker outside so that our system is going to be resilient against any initial disruption scenario you imagine. So in this paper, you can find more examples, but the most simple one is this so-called Daniels system. And then here on the first plot, I'm showing you this contour or boundary between this red and the white area for different occurrence rate of the hazard. And then here, these markers are representing some initial disruption scenario. And that this number means how many members fail in that corresponding initial disruption scenario. So if you have many failures in that scenario, of course, that is very less likely, likelihood is very low, so reliability is going to be really high. But since many components are gone, you have very low redundancy. And here you have a very small number of failure in the initial disruption scenario. It can happen very often, so reliability is low. But since only one member is gone, you have very large redundancy. So there's a kind of trade-off or contradiction between these two capabilities, right? So then here actually we found that if there's only one or two members fail, you don't have enough resilience for that system. So you should do something about them. And also there were 3 criteria, right? Reliability, redundancy, and recurability. So actually the recurability information can be incorporated into this beta pi diagram through colors or marker size, so that actually the decision maker can incorporate this third information. So actually I'm gonna just demonstrate this beta pi analysis through the same bridge, but this time under some different hazard, which is a fire from the tank truck. So here we assume that the tank truck had an accident and initiated a fire, and the fire occurred in the shoulder lane near cable, which are very critical ones. So actually heat impacts on cable will reduce the structural strength, and thermal expansion will just occur. And also, if some cable is damaged, load is going to be redistributed. So you might have some cascading failures too. So this is indeed a complex hazard occurring for the critical structure. So here, skipping all the details, we developed some probabilistic model for this heat radiation phenomenon, and also identify the uncertainty in this, and also using this probabilistic model, and also advanced finite element simulation of this bridge under heat, we were able to get this beta pi diagram. And then actually these numbers are actually the cable number. And we found that these cable, this light blue color here, they do not have enough resilience, especially due to this low redundancy. Because of this geometry, the adjacent cables had a larger exposure to this heat from the fire. So actually they do not have enough redundancy. So we should do something as an engineer to move these points outside that area. Maybe we can put some walls there, or wrap the cables with some of our fire resistant materials too. So for the sake of time, I'm going to skip this summary slide, but so far I just talk about disaster resilience and also show this analysis using this real cable stay bridge under fire hazard. And right now, actually, I'm just using this, further developing this one for the optimization. So here in this optimization scheme, we want to maximize recoverability while we are satisfying this socially acceptable reliability and redundancy for the system. Another application or further development is that we are applying to this next scale, which is a lifeline network. So here for this complex network problem, we check the beta and pi for each initial disruption scenario. And also using this so-called causality-based component importance measure we are developing, we were able to quantify relative importance of the components so that we can prioritize our actions on those. Okay, so then I'm going to move on to the next part. Here, my theme is on the risk intelligence. So actually, again, I'd like to recognize a great contribution from my current and former students, including Professor Ji-eun Byun, who recently joined the University of Glasgow, UK, as an assistant professor. So I will first talk about, explain what I mean by the risk intelligence, and then I will just demonstrate these 4 elements I identified of this risk intelligence: identification, integration, inference, and the implementation, using some examples. So in 2020, we had a conference, IAPSE conference in Seoul, and actually I was a moderator of this wrap-up session titled as a Toward Risk Intelligence of Infrastructures. And actually, after my brief introduction about what I mean by the risk intelligence, we had a very useful and helpful panel discussion by keynote lecturers. And then we just called it as Seoul Agenda 2020. So what is a risk intelligence? So actually, I'm just proposing or promoting this one as a future paradigm of a risk management of civil infrastructure. So beyond just simple risk analysis. So actually, we want to mimic how these human beings are identifying this risk, and also how integrate this information to identify and handle this risk, or how we infer or how we implement what we found to our actions. But now using this unprecedented amount of big data and the advanced probabilistic theories and the machine learning. So we have a chance to kind of achieve this risk intelligence these days. So let me explain this risk intelligence using this conventional risk analysis process. So we just collect data or information or knowledge, and then we just put them together in the form of some mathematical model that describe the phenomena or problem. And then by doing so-called analysis, we want to find out the output of this model for the given input, and we call it prediction. And based on this prediction, actually, we want to make a decision. But actually, as you know, in this data, information, or model, or our decision, there are lots of uncertainties everywhere. So if you make a decision based on this prediction result, which include lots of uncertainty, there is a risk. So all decisions you make will bring some risk to you. So in the traditional risk analysis, we just propagate these uncertainties through this engineering prediction process to quantify the risk of your decision. But in this so-called risk intelligence, actually, we want to have some more data-driven and automated and holistic and the real-time management of risk through these 4 elements, and also with some help from this data science and the computing power and artificial intelligence. So let me just explain these 4 elements using this same risk analysis process. First, identification means that actually we want to identify information knowledge from the given data. Okay, that is a so-called identification element. Second, integration is that all these knowledge or informations are embedded in a different kind of sources. Like some of them are in data, some of them in this model, some of them in this physics textbook. So actually, we want to integrate these different kinds of data, information, knowledge into some nice model. That's actually the integration element. Third one is that even though we have some model already, if you have some new data available from your observation or sensors, actually you want to have some probabilistic inference based on that. Simply, it's a conditional probability. So what if? What if you observe something? What's going to be the change in your prediction? That is so-called the inference process. And finally, actually, there's a big question about how we are going to then make a good decision when we have this risk analysis result in our hands. That is actually, that part I called implementation in my talk. So mathematically, these elements, 4 elements can be described as far as you can see in this table. But actually, if you just describe them in words, identification means that we want to learn from data. Integration means that we want to assimilate data with the model, or keep model better and better, or improve this model. And inference means that we want to update our prediction based on the new observation. And the implementation means we want to make a decision based on some quantified risk. So then what we need to achieve this new risk intelligence in future. So in a nutshell, first, you need to have some infrastructure, hardware, and platform that will enable this kind of very advanced task, like sensors, Internet of Things, communication, and the database, etc. But if you have just hardware, actually you cannot achieve this intelligence, right? Intelligence is a soft thing. So actually we must have this advanced probabilistic method, or this deep learning and machine learning method, so that actually we can process or exercise all these risk intelligence elements. So from now on, I'm going to briefly explain these 4 elements by some detailed example. But since I have just only 10 minutes, I'm going to just give you just brief explanation about what these are. So first, the example of identification. So we want to learn from data. So in this structural engineering area, there is some research field or area topic called the system identification. It means instead of assuming that we know everything about this structure, we want to just put this question mark to that structural system and want to figure out what is this structural system, like a parameter or damage or a deterioration in the system based on a measurement from the input and output together. So that's so-called system identification method. So it's very, active research area, and many researchers are working on it. But actually, if you want to perform the system identification under some extreme events, such as an earthquake event, actually, we want to do it in a probabilistic manner because there are lots of uncertainties. And also, we cannot do this by supervised learning because we cannot have a pair of input and output in this kind of problem. There are so many combinations and scenarios. So we want to do it some sort of unsupervised learning too. And also, of course, we want to do it quickly, like near real-time identification, because if earthquake occurs, we want to do some action very quickly, right? Or make a decision quickly. So in order to achieve these three goals, actually, we thought that we should get some help from the deep learning. So here I cannot describe all the details, but we trained this deep neural network model called variational autoencoder based on some structural analysis we performed before this earthquake occurs. And then in this online stage, when this earthquake event comes to you, we actually find some most similar case from our learning database to quantify this damage in your structural system and also locate damage in your system. So all the details can be found in this paper I published last year. But in this example, as you can see, in this 5A, 5-story, two-dimensional steel frame structure, for this damage scenario with the 3 columns, failures of 3 columns, these are light blue color there. Using this deep neural network, we are able to locate some possible damage location and also level of damage. There are some positive, false positive cases, but we don't have a false negative cases here at NIST. So this is going to be very helpful to do some quick inspection and also make some repair quickly. So we applied this similar method to the 3-dimensional frame structure recently, and we got a very good performance from this method too. Second, integration. Integration means that we want to integrate this variety of information and knowledge that have a different form into the same model, okay? So there are 2 different kinds of approaches, like model-based prediction and the data-driven prediction. But as we all know, they have their own pros and cons. So actually, it would be very nice to keep improving our model based on some available data, right? So that is one way to achieve this integration element in our risk intelligence. So here I'm going to give you some example. So in this online dynamic learning framework for deterioration prediction, we use some particle filter. So I believe many of you are familiar with Kalman filter. That's one of the Bayesian filters available out there. So using this Bayesian filter or particle filter, we can have 2 kinds of update. So time update and the measurement update. Time update means that we want to predict our deterioration at the next time step using this existing model. And then the measurement update means that if you have a measurement about actual deterioration or related environment, actually you can adjust or calibrate your prediction based on the observation result or measurement. So that is a measurement update. So if you use any Kalman or Bayesian filter, you are performing these 2 kinds of update at every time step. But in this particular study, we wanted to update these parameters in this deterioration model, corrosion model. As you can see in this plot, for the same model, depending on what parameter value you use, you can have a great variability in your prediction as the time goes on. But actually, we assume we know these parameters exactly, but that's not true. So when we apply this filter technology to this problem, instead of just calibrating our result based on the observation, or just improve or predict what's going to happen in the next time step using this same model, we kept improving these green parameters in the model too, using this particle filter technology. So in this example, you see this couple of plots. This blue one is your prediction of the thickness of your steel plate or level of deterioration as time goes on. Of course, since your assumption about these green parameters in the deterioration models are wrong, your long-term prediction is quite, inaccurate. Okay. And then this dashed line is actually true, state of your structure. But if you use this particle filter, whenever you have this observation in the field test, from the field test, you are going to adjust or calibrate your prediction. That's a Kalman filter thing. But at the same time, actually, as you can see at the bottom, we kept improving the model parameters. So it means at the same time, your model is getting better and better. So this data and model is being assimilated. And then actually we stop our inspection at year 22. So at this moment, from now on, actually, we don't have a chance to calibrate our result because we have no real data. But since we improve our model from year 0 to year 22, our long-term prediction is also quite good. So that's actually the benefit of this, improving our model based on the data through this integration element. Third one is inference. This is a most sophisticated one, so I'm not going to spend too much time. But basically, inference means that we want to compute conditional probability. The conditional probability based on some observation or new data or new evidences. So here in this network example, so for benchmark transportation network, we constructed this so-called Bayesian network model, in which each node represents some random quantity in your problem. For example, magnitude of the earthquake, the location of the epicenter, or the deterioration state of each component in your network, and also state of the road after earthquake event, X1 to Xn, and I1 to In are inspection result, and Xn plus 1 is the state of your system, whether these two nodes are connected or disconnected. So you can construct this kind of graph-based model using Bayesian network methodology. So one powerful feature of this Bayesian network is that you can compute the probability of any node, but whenever you have new evidences for any node, you can update the probability of all the other nodes. So updating means that you can compute conditional probability. So here in the following slides, I'm just giving you some details about this Bayesian network and also how we improve this one, especially the Dr. Bian at the University of Glasgow, how we improve this one such that it can be applied to the large complex systems. So as a result, as you can see at the bottom, so the CPIM is one of the measures of the component importance. So these red markers are actually the prediction or probabilistic measure of this component importance for the different nodes. But then when you have some inspection results, these importance are actually going through significant change. Those are kind of probabilistic inference. So based on some new inspection result, you are improving or updating your prediction about the performance of your structure or components. And finally, the fourth element is implementation. So this is related to decision making. So how can we make a best or optimal decision based on the risk we quantified? So that is actually very quite active research area called RBDO, Reliability-Based Design Optimization. So if I explain this one by one figure, if you ignore the risk, in this optimization problem, you are going to be happy with this black marker, okay? Because that's the point in this design space, which is safe, and also it's minimizing this objective function. But since there is uncertainty, as you can see, there's a significant likelihood that you are going to have this failure. So we cannot eliminate the risk, but we can manage it. So in this optimization scheme, we describe this constraint probabilistically. So we want to minimize something or maximize something while probability of failure is lower than some value. So that is so-called RBDO. So here in our particular approach, we developed this so-called quantile surrogate-based method so that we can handle this computational cost, huge computational cost in this RBDO. And using this particular method, we got the same or similar optimal design, while we are calling this computation simulation much less times. So by comparing our performance with the existing RBDO method, we found that this one is more efficient and also still accurate in terms of optimality and also satisfying this constraint on the risk. And also in this second version, QS2 AGP, we use this sensitivity information so that we can use this more efficient optimizer called the gradient-based optimizer in our optimization algorithm. So as you can see in this figure, we were able to reduce this computational time dramatically using the second version. And also we were able to cover large number of design variables or some parameters. So actually we can apply this kind of algorithm to optimize topology or shape of the structure while we are managing the risk at a certain level, target level. So here, this is a summary of the second part. So by identification, we can learn better about the structure system or civil infrastructure from the available data. From integration, actually, we can get the maximum information knowledge from data, information, and given model through the data assimilation. And also we can infer, it means we can predict better if some new observations available through sensors or some other sources. And finally, we can make a good and optimal decisions while we are satisfying constraint on the given risk. So actually, I believe if there are some audience who are requesting, the PDF version of this slide will be shared. So this is kind of ongoing and future research topic related to each element. And also these are the reference information about the works I just, briefly presented in the second part of the presentation. So, but for purpose of this talk is just to talk about these two main themes, disaster resilience and the risk intelligence. So I was not able to cover all the details, but I hope that with this example, you got a better idea about what I mean by these two main keywords or themes. Thank you very much for your attention and also opportunity to talk about my research, and I'll be very happy to answer your question. Thank you very much.
Thanks a lot, Professor Song, for the extremely fascinating topic and the presentation, and for your time that you dedicated to us to share your research. I think we could go on for probably hours and hours talking about your work and the work that you do with your research team. But in the interest of time, I've got a question which comes from myself, and is more of a general question related to the many parts of the problem that you've investigated and you've showed us. Which of the several components of between identification, training of the VAE, the understanding of whether the results make sense in the lack of a full scenario, the improving of the model, and the computation of conditional probability based on new data is the part that you think is more, not just uncertain, but more difficult to catch. I'd like to know more of your opinion, whether there is any of those parts that you think depends more on the understanding or external conditions that change the system, if you see what I'm saying.
So you mean among these four elements, which one is
Yes.
more challenging to achieve?
Yes, and to grasp.
Okay.
Or requires further adjustment each time something happens.
Yes. So I think that they're all different and challenging, difficult and challenging. And also, as I said, many researchers have been already working on their research to achieve these kind of elements in our risk intelligence or risk practice. So they have their own challenges. So it's very hard to compare which one is more difficult. But in terms of how to incorporate this kind of new data available at every time point, the fourth one, implementation part, it is actually the optimization. So it will be very difficult to incorporate this kind of time element into it. So, and also, and this, I don't have much experience about it, but so far I didn't have that kind of time element in this, my work on the RBDO. But for the other three, actually, we have that kind of data we collect at every time, discretized time point in our applications. For example, in this system identification example, actually we use time series data. So let me just go to that slide.
Thanks.
So here, I did not have enough time to give you details, but in this arrow, the vertical arrow is representing the time step. So at every time point.
Sorry, you are not presenting. We cannot see your
marker.
Your screen.
Can you see that?
No.
No?
No.
Oh, let me just.
Now it's loading.
Yes.
Yeah.
See it? Okay. All right. I think I stopped sharing this slide at some moment. Okay. So as you can see in this figure, this vertical arrow representing the time step. So it means during the earthquake event, actually we are going to get this kind of dynamic response of a structure at every discretized time point. So actually we are already kind of incorporating this data at every time point in that axis. In this integration part, in this example, time steps are kind of larger because we are talking about the year. And also this kind of decision doesn't have to be as rapid as the previous one because the deterioration usually goes on very slowly. But actually, if it's a kind of more extreme one, actually there is no technical limit about how often we can incorporate this data on the time axis. For this Bayesian network, actually there is a method called the dynamic BN. So dynamic BN means that we have this kind of Bayesian network model for every time point. So then actually these kind of Bayesian network at a different time points are going to be connected by another set of arrows to describe how this system change over time. So it is possible, but I don't think we can do it as often as the first case.
I see.
Did I answer your question? So
yes, Yes, you did answer my question. And clearly, I mean, as I said, we could go on for probably other 10 hours discussing each and every slide.
It would be my pleasure. Yes, it would be my pleasure.
Yes.
Please,
and I was also very... Mm-hmm.
May I make a question, please, Mr.
Absolutely.
Valentina. Okay. I want to know, Dr. Song, in what moment or how is it possible during the process of the analysis to incorporate the sensitivity of the results on data? I mean, we can have different quality of data, quality and quantity of data. And is there any point of control along the process to know, to identify the risk of use one or another kind of data?
That's an excellent question, and thank you very much. So I think that question is most related to this second element, integration. Mm-hmm. Here in this data assimilation, it is very important to know the quality of the data you are getting. So here, you see this measurement update action, right? So actually, based on the new measurement about some state of the condition of your structure or some environmental effects surrounding your structure, you are going to adjust your prediction about the next time step. But as you said, if our measurement has lots of noises, actually this adjustment is going to be also inaccurate. It means we should not rely too much on this information from the measurement. So then how much weight should we assign to this new information from the measurement? So that is actually quantified by this variance or covariance matrix in this formulation. So actually, as an engineer, you should know a priori how good this measurement or data is. So actually, we can quantify it in this system. So then, if you know that this data is noisy and the sensor has lots of error, actually this adjustment is going to be more conservative. So there's a way we can incorporate that.
Okay, very, very clear. Thank you.
Thank you.
I don't see any further question on the chat box, but if anyone has any other question, that Professor Song can take any question offline if needed. And I will probably have further questions to ask you, so I'll reach out to you personally if you don't mind.
Sure.
And I think we have now reached the end of the webinar. I'd like to thank Professor Song for his extremely insightful presentation and for your time. And thank you all for attending the webinar. The recording will be available soon, and we will share the details so that we can make good use of your lecture, Professor Song. So thank you very much all for your attendance.
Thank you very much, Valentina. You have done a very good work in contacting and getting the participation of Dr. Yu-Ho Song. It's very impressive, and I think that we start the year in a very good way.
Yeah.
And I want to remark the presence with us and in the room of Dr. Gong Ke, that is the past president of WFEO, immediate past president of WFEO, and that are always supporting our committee. And some members of the committee too, Dr. Tin Chi Sao from Taiwan, Dr. Hisham Ghazali, and all the people that are accompanying us. I am quite surprised that are several Latin American names. That it means that the webinar is so interesting that they have woke up very early in the morning. So thank you very much to all of you. We there is also on the floor Professor Alexander Kunitsky from Switzerland, always supporting the members of the activities of the committee. Dr. Son, thank you very much. This has been very, very interesting, even for people not in the speciality, very specific. Also to Valentina for the organization. Again, thanks to our technical people from the Peruvian Association of Engineers. And we will be announcing the next activities very soon. Thank you very much, and up to the next time. Have a good day and a good night.
Thanks a lot.
Doctor, quería aprovechar para tomar la foto, por favor.
Yes,
pueden...
please.
Yes.
Yes. Una mirada a la cámara, por favor, y una sonrisa. Muchas gracias.
We are not in full camera.
Perfecto.
We start looking at the... Yes,
Perfecto,
yes.
muchas gracias. Por favor, pueden despedirse, activar sus micros para despedirse de nuestro público que nos ha acompañado el día de hoy.
I think I understood. You took a photo, right?
Yes.
Thank you very
Yeah.
much.
Así
Thank
es,
you.
correcto, sí.
See you.
Tomamos la foto.
Gracias a todos.
Bye. Bye.
Bye.
Hasta luego. Para nuestro público tenemos la grabación de este webinar. Igual vamos a compartir en estos momentos el link para que ustedes puedan ubicarlo en nuestro canal de YouTube, así como también en nuestra página web. Estamos compartiendo la pantalla, creo que... Permítanme un segundito, por favor.